Welcome to the Explainer. Today, we're diving into invisible particles and visible changes, chemical reactions. We are officially taking on the role of matter investigators. Our mission, to look at the everyday world around us. Things breaking, burning, melting, rusting, bubbling, and decode what's actually happening on a microscopic, completely invisible level. Just think about all the wild transformations we see every single day. A piece of raw dough goes into an oven and comes out as a fluffy cake. A shiny new bicycle left out in the rain turns reddish-brown and flaky. Or hey, a glow stick snaps and suddenly radiates neon light. How do invisible particles explain all these incredible visible changes happening right in front of our eyes? Well, that's exactly the case we're going to crack today. Section 1. The Visible Change Myth. As investigators, we first have to tackle a major mystery and confront a really common trap.
Think about holding a glass of ice water on a sweltering summer day. You watch the solid ice cubes slowly shrink and melt away into the liquid. Or imagine holding a thick piece of construction paper and hearing that harsh, loud rip as you tear it straight in half. Now, if you can literally see a change happening right in front of your eyes, and if the object looks drastically different than it did just a second ago, does that automatically mean a brand new substance was created? Does a totally different outward appearance always equal to completely different chemical makeup on the inside?
Okay, we need to bust this myth right now. Just because something dissolves in water, breaks into jagged pieces, or melts from a solid block into a liquid puddle, absolutely does not mean it went through a chemical change. We call this the visible change myth. See, our human brains are naturally wired to think, hey, it looks new, so it must be new stuff. It's such an easy trap to fall into. We often just assume that because we can see a dramatic visual difference, the fundamental building blocks of that matter must have changed. But as we're about to discover, our eyes can be easily fooled. Section 2. Defining the two changes. To solve our cases properly, we need to lay down the absolute rules of the investigation. Let's get our definitions perfectly straight. First up, a physical change. This is a change that alters the form or state of a substance, but emphatically not its chemical identity. Think of a physical change like changing your clothes. You might put on a heavy winter coat, or you might change into a summer swimsuit. Your outward appearance changes drastically depending on the weather, right? But underneath those clothes, you are still exactly the same person. You haven't magically turned into someone else. Water is the perfect example here. When it's freezing cold out, H2O puts on its heavy winter coat and becomes solid ice. When it warms up, it changes into its everyday liquid water suit. And if you boil it, it throws on an invisible vapor jacket and becomes steam. Whether it's ice, liquid, or steam, the invisible particles haven't changed their fundamental identity. It's literally just H2O wearing 3 different outfits. When you tear paper, it's just paper in smaller pieces. Dissolving salt in water, it's still salt, it's still water, just mixed together.
On the flip side, a chemical change means the invisible particles have completely rearranged to produce a brand new substance with entirely different properties. If a physical change is like changing your clothes, a chemical change is like taking a giant Lego castle, completely breaking every single brick apart, and snapping them all back together to build a spaceship. The original stuff, that castle, is completely gone. The individual pieces have shuffled around and bonded in entirely new ways to create a totally different object. During a chemical reaction, the original particles break apart, shuffle around, and form new bonds. The stuff you started with is gone forever, and completely new stuff has taken its place.
Which brings us to Section 3, evidence of new substances. If we can't actually see these invisible particles rearranging with our naked eyes, how do we know a chemical change happened? We have to look for physical clues, hard, observable evidence. And here is our ultimate investigator's checklist. You'll want to pull out your magnifying glass and look for 4 primary signs. First, an unexpected color change. Now, I don't mean mixing blue and yellow paint to make green. I mean something totally unexpected, like a crisp white apple slice sitting on a counter and suddenly turning a sickly brown, or a shiny silver bike chain turning flaky red. That unexpected color shift is a massive clue. Second, gas production. Are there suddenly bubbles fizzing and foaming up? Think about making a classic homemade volcano. You mix baking soda and vinegar and boom, massive amounts of carbon dioxide gas bubbles erupt. Third, a temperature change. Does the substance suddenly get really hot or freezing cold without you actively putting it on a stove or in a freezer? If you've ever snapped one of those chemical hand warmers on a freezing day, you know exactly what I mean. It's basically a chemical fire burning without a flame. And fourth, precipitate formation, which is really just a fancy scientific way of saying a new solid suddenly forms out of nowhere. Imagine pouring 2 perfectly clear liquids together, and the second they mix, a heavy, bright yellow powder suddenly appears and snows down to the bottom. If you spot these clues, color, gas, temperature, or a precipitate, you've likely caught a chemical change red-handed. Section 4, melting butter versus burning wood. Let's step into the interrogation room and put two suspects side by side.
We've got melting butter on the left and burning wood on the right. Let's run down the checklist. Look at the butter. Leave a stick of butter in a hot pan and it turns into a puddle. Did the color drastically change to something unexpected? No, still yellow. Did it fizz and produce gas? No. Did it create a new solid precipitate? No. It just changed its state from a solid block to a liquid puddle. If you cooled the pan down, it's just solid butter again. Same identity, so melting butter is purely a physical change. But now look at the burning wood. Throw a log onto a roaring campfire, and it gives off massive amounts of heat. Check off temperature change. It releases thick smoke into the air. Check off gas production. And it turns from hard brown wood into crumbly black ash. Check off color change. The wood gives us undeniable multi-point evidence of a chemical change. The original wood is gone, and the invisible particles have rearranged into completely new substances.
Section 5. Your final challenge. All right, it's time to hand the detective badge over to you for one final case. I want you to look closely at two everyday things, a piece of slowly rusting iron and an aluminum soda can that's been crushed flat on the pavement. Mentally pull out your clipboard. Using the exact 4-point evidence checklist we just learned, how would you classify rusting iron versus a crushed aluminum can? Don't just guess here. Think deeply about the invisible particles. Think about the identity of the substances. When that shiny iron turns flaky, orange, and red, what is actually happening? When that soda can is stomped flat under a shoe, did its chemical identity change? Or is it just wearing a different outfit? What exact clues justify your answer? Take this evidence, build your case, and never stop investigating the invisible world around you. Because right now, chemical reactions are happening absolutely everywhere, even breaking down the food in your stomach and powering the muscles in your body as you listen to this. The invisible world is always in motion.